analyzed the linear dynamics of optomechanical systems last time, and so as a natural next step I want to turn to the nonlinear dynamics. That is, we remain in the classical regime first, but we want to look at the nonlinear dynamics. In particular, we want to look at what happens if the system really becomes unstable. And we already learned it can become unstable because you can not only cool such a system, but you can also switch to the other side where the light field actually puts in extra energy into the mechanical motion. And so if that overwhelms the friction, then you can go into a regime of what we call self-induced oscillations. So that's what we want to discuss. So just to remind you, the idea was that the full damping rate contains the intrinsic mechanical damping plus some extra contribution induced by the light field, which is proportional to the intensity of the incoming laser beam. And this can also be negative depending on the detuning. If the laser beam is blue detuned, then it submits some extra energy to the mechanical system. And so if this is negative, and then if even the whole damping rate becomes negative, then you can go into an instability. Because what happens in such a case, again just to remind you, is that if you have any tiny initial fluctuations to start with, for example thermal fluctuations, then because you have negative damping, these blow up exponentially. And only when the amplitude of these oscillations becomes large, then this linear analysis is no longer valid. And that means there will be nonlinear effects, and these nonlinear effects make the amplitude of these oscillations saturate. So one of the reasonable questions to ask is, what determines this final amplitude of the oscillations? Well, and obviously, a priori this amplitude will be a function of all the different parameters we have. The mechanical parameters such as the mass, the frequency, or the mechanical damping. Also the parameters of the light field, such as, for example, the detuning or the damping rate of the photons, kappa, or also the strength of the laser drive, because of course if you switch off the laser drive, then the amplitude will be zero, there will be no such oscillations. Okay. Now, the first thing you can do is simply simulate the equations that we wrote down last time on a computer and convince yourself that first, indeed, this is true, this scenario happens, it does saturate. And second, these oscillations for typical parameters are still very much sinusoidal, with only very tiny deviations. I mean, you are not guaranteed that this looks like a sine of omega t, but there are only tiny deviations. And furthermore, the frequency of these oscillations is practically identical to the unperturbed eigenfrequency of the mechanical system. Again, this is not guaranteed, and you can choose parameters such that is no longer true, but for typical parameters this is true. So the ansatz you can make for our purposes is simply that you have this sinusoidal type oscillation. It will have some offset x bar, which is not necessarily the equilibrium position of the oscillator that is not coupled to the light field. This can be shifted, and we will discuss this. Plus some as yet unknown amplitude A times cosine omega t, or sine omega t. Because another observation is actually that the phase of these oscillations is not fixed by anything. So now the first thing you can do is assume that the mechanical oscillations have this form. What happens to the light field? This is an important question. And even though the mechanical oscillations are very simple of this form, the light field undergoes a more complicated dynamics. So again, I will plot x versus t. I do have some x bar around which it oscillates. And then, depending on my detuning, at some position I will have my optical resonance. So some position of my mirror or cantilever will correspond to the laser being in resonance. So that is actually if x times the optical frequency divided by L, that was the frequency shift, plus delta, the detuning, equals 0. Then you are at resonance. And so now what happens with the light field? Well, what I want to plot is simply the intensity, that is alpha squared, as a function of time. And now imagine that everything is completely adiabatic, so the motion is very, very slow compared with the time scales of the electromagnetic field. Then, whenever you pass through the resonance, the intensity would shoot up. So that would happen here, and it would happen here, and here, and there, and so on. And then it repeats periodically. Now, if everything is adiabatic, this would simply be a Lorentzian, and then there would be the next Lorentzian and so on. But things are not necessarily adiabatic, and this is important for this purpose. And so what really happens is that the light intensity shoots up, and then it decays, but in a relatively complicated pattern of some ringing oscillations that look like beating. And then it shoots up again, and again. Decays in this kind of oscillation pattern. And then the whole structure repeats. Okay. And so the most important characteristic now is the following. If I look at the radiation pressure force that is proportional to alpha squared, then I can ask, what is the power input provided by the radiation pressure force? Now, if I know an external force acting on a mechanical system, then the power input will be the force times the velocity at each instant of time. So that is the instantaneous power. And then if you want to ask whether overall there is some power input, you would average this over time. And it turns out that if you plug in this relatively complicated pattern for the intensity, that is the force, and take into account the simple pattern for the velocity, this time average is non-vanishing. And it's positive. It will be positive in a case where indeed we do have this instability, because then the light field must introduce some extra mechanical energy into the system. Okay. So that is already the basic idea. And the question is now, where are the two equations that we need to find these two unknowns that are the amplitude, most of all, plus also this offset? So we need two equations. Well, the first one is simply the following, that the power you put into the system by the light field must equal the power that is dissipated by friction. That is reasonable. So I want to call this power balance. So what is the friction force? Well, it is the mass times gamma times x dot. This is the friction force. And if I want to calculate the corresponding power, I have to multiply this force with the velocity, so I get velocity squared. And again, I want to average this over all times. That will be the power lost by friction. That will be the power put into the system by the light field. And of course, both sides of this equation will depend on the amplitude of the oscillations, because if I increase the amplitude of these oscillations, then also the light pattern will change, therefore the radiation pressure force as a function of time will change, the left-hand side changes. And the right-hand side also trivially depends on the amplitude, because if I make the amplitude larger, the velocity simply gets larger. So that is the first and most important equation. We still need a second equation to obtain this average offset, but that is also easily motivated physically. Namely, if the trajectory looks like this, then on time average, the force provided by the radiation field should equal the restoring force of the harmonic oscillator. And that is simply m omega squared, that is the spring constant, times x bar. That I would call force balance. So it's lucky that we found two physically motivated equations to obtain these unknowns. And in the following, our task will simply be to find an expression for the radiation pressure force, to find an expression that contains this rather complicated pattern that you would observe on a computer. Okay, so now this is a little exercise in nonlinear dynamics, but before we come to that, there will be a little exercise in making equations dimensionless. Because the idea is we have equations that depend on so many parameters, not all of which enter in any essential way. So the idea is that we want to make the equations dimensionless, and then we identify, in this case, only 4 true dimensionless parameters that really change the structure of the solution. Okay, so let me write down briefly again the equations that we wrote down last time. That was the mechanical equation, that is simply Newton's equation. And then second, there's the equation for the light field, for the amplitude alpha, and that simply obeys the equation of motion for damped and driven harmonic oscillator expressed in this complex amplitude. So there was a detuning delta, which is the difference between the laser frequency and the bare optical resonance frequency, plus there's some extra frequency shift induced by the displacement. Then there is some damping, and finally there's some drive. And we chose to characterize the drive by introducing an amplitude alpha max, and it turns out that if we are right at resonance, then alpha will be equal to alpha max. Okay. So the question is now how to make such a system of equations dimensionless, and of course there are many different choices. Essentially always you have time, length and mass, and you can change these units, so to speak. And the way I want to think about it is I take these old variables, for example x or t, and turn them into new dimensionless variables simply by, for example, dividing by some time or dividing by some length which I choose. And of course I could choose any length or time, but it's very convenient to pick some physically relevant time and length scales. For example, if I look at the time and I want to arrive at a dimensionless time, I could make things such as, for example, the mechanical frequency would become 1. That is one possible choice. But the choice I want to take here is that kappa in the end becomes 1. So what I do is I take my old dimensionful time and multiply it with the weight kappa. So this essentially, the new time measures how many photon decay times have elapsed. It's a dimensionless quantity. Likewise, for the new position, I want to take the old dimensionful position and divide it by some delta x, some conveniently chosen delta x. Now what's my choice here? Well, what I do is I look at the optical resonance peak as a function of displacement, and I look at its width. And we know what its width is like, namely in frequency space the width is simply given by kappa. Kappa is the photon decay rate. Now I have to translate this into a displacement, which I do by this formula. I want to make this equal kappa, so x better be equal to L over omega opt times kappa. And that is the width of the resonance in real space. And so I divide all x by this, and that is a reasonable choice because, for example, if my oscillation amplitude becomes larger than the full width of the optical resonance, then apparently things have to change. And lastly, I can choose a new mass, but here I will take the very convenient option, just setting the mass equals to 1. So I take the old mass and divide it by itself, and that gives 1. Okay, so these are all choices that I would have generically: time, space and mass. But then sometimes I can simply, without paying any price, introduce additional simplifications. For example, I can say that my new light field amplitude, which is dimensionless anyway, I obtain by taking the old one and dividing it by alpha max. This simply means that I essentially set alpha max equals 1, and that I can do as well. Okay, so what is done next is I would express t by t nu, x by x nu, and so on, and then I would insert this into the equations above. And afterwards I properly divide both sides of the equations and I group all prefactors into dimensionless combinations. And so I write down what that results in. But before I write it down, I want to save writing, and so I will rename my time, which now is t nu, into t. So t from now on will be the dimensionless time. So I will first insert into the equations and then again rename t nu into t, and so on. So what does it look like? First, the dimensionless equation for the light field. Time derivative of the new alpha will be I times, well, there was a detuning delta which turns into a new dimensionless detuning delta, which is simply the old detuning divided by kappa. And then there is this combination, but it simply turns into x, into the new dimensionless x. And then I have my decay here occurring at the rate kappa, but kappa has become 1. So I have minus 1 half times alpha. And then finally I have my driving, still with an alpha max initially, but since I also rescaled alpha, this becomes 1. Okay. So this is the dimensionless equation for the light field. And then there's another dimensionless equation for my new dimensionless position, which no longer contains a mass, but it contains alpha squared from here with a prefactor. I call it P, and I will tell you immediately what P is. P is a dimensionless combination of all the quantities and is proportional to the laser intensity. Minus the restoring force, and there's a new dimensionless frequency, which I also will write down, minus gamma times x dot, gamma tilde times x dot. Okay. So now omega tilde and gamma tilde are simple. They are just re-expressing the old frequency in terms of gamma, in terms of kappa, excuse me, because that is our new frequency scale, and gamma tilde would be gamma divided by kappa. So that is reasonable. Now P contains all the parameters in one big dimensionless combination, and that is h bar alpha max squared divided by m delta x squared times kappa. So these are the equations. Of course, structurally they have exactly the same form, only they have a form that looks a little bit simpler than before. And what they tell us in particular is that all our results will only depend on 4 dimensionless parameters. This will be delta tilde, P, omega tilde, and gamma tilde. All the rest will just rescale the curves. So if someone calculates the solution for a set of parameters that keeps delta tilde, P, omega tilde, and gamma tilde the same, only all the parameters change individually, but these dimensionless combinations are the same, then the resulting curves will look exactly identical up to a rescaling of the axis in the plots. Okay, so P, so to speak, is the drive. Omega tilde is the frequency, the mechanical frequency. Gamma tilde is the mechanical damping. And finally, delta tilde is the detuning. And you automatically know that only these will be important. You know, for example, that in quantum electrodynamics there's the fine structure constant, and there's only the finest structure constant as the only dimensionless parameter. So if you keep the fine structure constant, change all the other parameters, everything will just be rescaled. Maybe the radius of the hydrogen atom will blow up, but everything will just be rescaled. Okay. Now, what we want to do next is we really want to eliminate the motion of the light field. This is something which we already did for the linearized case, only here we want to be more ambitious. We want to eliminate in general the motion of the light field for any given trajectory x. And luckily this can be done. once again, the equation we want to solve is the equation for the light field dynamics that contains delta tilde plus x of t times alpha plus So at first sight this might look a little bit difficult, but in principle this is an equation of the following form. You have some a dot of t equals some, say, lambda of t times a of t plus some external forcing. And so an equation of this type you can always solve, because you can always say, if a force acts at some earlier time, let's call it t prime, then once it has acted, it will evolve according to a dot equals lambda times a. Yeah? But the solution to this is simply an exponential. E to the, and then if lambda is really time dependent, an integral from t prime to t lambda of some time variable. So that is the solution if only at time t prime I had a little force applied, but if at any arbitrary earlier time I have some force applied, I have to integrate over all the contributions. And that would give me the value at a of t. Plus there could be a solution coming from the initial conditions, but if I go back to time minus infinity, then these will have decayed away if lambda has a real component that is negative, and so this is the only solution that remains. Yeah. So this is something which we can solve. And so we can apply this to the equation given above. Now f is very simple, it's just 1/2. But then I really have to integrate over all times. And now there are two parts of the equation. If I forget about x of t, the rest is simply time independent. That would correspond to a time independent lambda, and for a time independent lambda I can simply carry out the integral in the exponent, which just gives me t minus t prime, the difference in terms. So I would have e to the, now I just read off, e I delta tilde minus 1/2 times t minus t prime. That is one part. And then for the rest I really need to do the integral. Integral from t prime up to t I times x. Okay. So this is the complete solution for the light field amplitude for any given particular trajectory that the mechanics undergoes. And that is a scheme which is fairly general. Whenever I have a reservoir, like here it would be the light field, I want to eliminate it in terms of the given completely arbitrary trajectory of my system. And then in turn I want to find out what that means for my system. Okay. So the next thing I could do in the general scheme would be to take alpha squared and reinsert it into the equation of motion for the mechanics. And then I would find that the mechanics experiences a radiation pressure force that depends in a non-local in time and non-linear fashion on the previous motion of the mechanics. Okay. But in this general fashion, of course, it's really complicated, and also it wouldn't be efficient numerically. It's much more efficient numerically just to solve the coupled system of equations of motion. But we can be a little bit more specific. We can say we know an ansatz for our mechanical motion. We know that, say, from numerical experiments, for these systems, for the given parameters, it's just sinusoidal motion. And now I am already in my dimensionless units, so here I have omega tilde, and t would be dimensionless a, and x bar also would be dimensionless. So now if that is the case, I can plug this in up here and really carry out the integral and the exponent. So then the integral will be one simple part, that is x bar times the difference in times. That has a structure similar to the one appearing here. So we can combine these in the end. Plus the integral over the cosine, which will give a sine function. So now that was one integral, the integral in the exponent. Unfortunately, we still have to integrate this exponent, this exponential over all times. And so how would we go about doing this? We have something of the form integral dt prime e to the something, which is simple, and e to the sine omega t prime, basically, with some prefactor. Okay, so here the solution is the following. One can always expand an exponential of a sine function in terms of a Fourier series, and the Fourier coefficients are known to be Bessel functions. And once you have a Fourier series, then you can easily carry out the integral. That's the idea. So what I want to use now is that e to the minus I a over omega tilde sine omega tilde t prime can be written as a simple Fourier series. So that would be e to the I n omega tilde t prime. There are all Fourier coefficients with arbitrary index n times jn of the prefactor here, minus a over omega tilde. And so the j would be what people call the Bessel function of the first kind. Okay, and once you believe this, you are basically done. Because now all the integral is really only an integral over a simple exponential. For each term in the Fourier series will be a simple exponential. So what I need now is simply that the integral dt prime of e to the I times some, call it mu t minus t prime, and mu would be the combination of this delta tilde and the 1/2 and x bar times a part of this Fourier series will simply be the following. I expand this into t prime minus t plus t, pull out the e to the I and omega tilde t in front, and the rest is evaluated very easily. So it only has a contribution from the upper boundary of the integral, and I can just copy the prefactor and the exponent into the denominator. Okay, so now you see in the end we will get a Fourier series. The Fourier coefficients are essentially already there. These are the Bessel functions and this 1 over this ratio there. And so what we get in the end is alpha of t equals this Fourier series with some coefficients alpha n, which I will write down, which are these combinations of Bessel functions, and the ratio. And I will also pull out an overall phase factor, which is also very simple. So now these alpha n, how do they look like? Well, I just have to copy from there. This is Jn, the Bessel function containing the amplitude of the motion, divided by n omega tilde minus I x bar plus delta tilde plus 1/2, and then there was still a factor of 1/2 in front. And the theta of t, this is simply one part of the exponent, and that was a divided by omega tilde times the sine function. Not very important. It's not very important because in the end we will only be concerned with the intensity, that is alpha squared, and then the phase factor will not matter. So this is the best I can offer, the most compact expression for what the light field does. And as you see, it does depend on the amplitude, obviously. It does depend on the detuning, and it also does depend on the offset, which of course we don't know. So the offset and A are the parameters which we wanted to get, and the light field dynamics depends on both of them. And so in the end we will have to solve our two equations, power balance and force balance, in such a way that they are fulfilled, and then that gives us A and X bar. Okay. Now, for these two equations, what we really need is the average force, so alpha squared averaged over time. And we also need the average power input, that is alpha squared times the velocity averaged over time. And that I want to write down now, and as you can guess, if I take alpha squared and average it over time, only a few Fourier coefficients will survive. So for example, what's the average intensity? Well, I take the expression for alpha of t. The phase factor doesn't matter. It vanishes when I take the drops out when I take the magnitude squared. And apart from that, I just get a double sum. But now, of course, the idea is that time average of any oscillating exponential will vanish automatically. So the only term that remains is the one where n prime equals n. And so this retains a single sum over n alpha n squared. And so, for example, if I want to write down my force balance equation, then the radiation pressure force was P times that equals the restoring force. Now mass is 1 and I have omega tilde squared times x bar. And the idea is that the left hand side also depends on the amplitude and x bar. So that is one of the two equations in principle we have to solve. Okay. Now what about the average power input? This is slightly more interesting. What I need to get is alpha squared times the velocity. Now, the velocity is simply sinusoidal. And again, I can expand alpha squared just in this manner, copying the formula from here, but now I have to multiply with the exponentials that come from the sine function. Okay, so what this means is that now, in order to have a non-vanishing time average, no longer do I need n equals n bar, but I need n bar equals n plus or minus 1, depending on which factor from the sine I put in. So that's the idea. And so in the end, again, I can reduce this to a single sum. And I find that this is minus a omega tilde divided by the 2i from here, times the sum over n, alpha n plus 1 star, alpha n, minus alpha n star, alpha n plus 1. And now this is basically a quantity minus its complex conjugate, so it's the imaginary part of a complex number. So this is the most compact expression I can give for the average power input. Again, the amplitudes depend on the Fourier amplitudes alpha depend on the amplitude A and the offset x bar. So now I can write down the power balance equation, because at least in principle I know the ingredients. what we have is that P times alpha squared x dot, this is the expression I just calculated, equals the frictional loss. But x dot is just written down here. If I square that, I get a square omega tilde squared, and the average of the square of a sine function is just 100. Okay. And now there's a convenient way to re-express these things. Namely, I can exploit the fact that I know alpha squared times x dot, even though it's a complicated expression, it does not depend on the power p. That doesn't enter anywhere there. It also does not depend on gamma. That also doesn't enter anywhere there if you look back into the expressions for the alpha ring. So it's better to separate off this dependence. Then I can say, aha, alpha squared times x dot divided by what I have here, equals gamma divided by p. So this depends neither on gamma nor on p. And that's a good feature. In particular, I know the following. Whenever I can allow myself to ignore the dependence on x bar, for example, because the shift is not really that large, x bar is practically zero, near the usual equilibrium position, then this left-hand side does not even indirectly depend on p, not even via x bar. And so that means this is an equation where the left-hand side is completely independent of both gamma and p. It's only dependent on the amplitude in that case, and the only dependence on gamma and on p comes in via this ratio gamma over p. So that, for example, tells me that in this case there's even one less parameter. We had 4 dimensionless parameters, but this tells me that in that case I only have a dependence on the ratio of gamma over p. And that's also a prediction. So if someone increases the damping but also increases the laser power by the same amount, you will just see the same pictures. Okay. So now I want to, well, this is as far as we can get. And now I want to plot the solution graphically. So the idea is just to treat this as an equation that has to be solved. I want to plot essentially the left-hand side in the parameter plane, where I keep as a parameter the amplitude and some other experimental parameters, such as the detuning. That's the idea. And in order to evaluate this on a computer, that would be very efficient to just plug in the Fourier components which we have available. So it's much, much more efficient than really solving the equations on the computer and waiting for things to settle down and looking at the amplitude. So what I want to do is plot the left-hand side of this equation, and then I just need to look at the contour lines, because in the end, the ratio on the right-hand side will pick one of these contour lines according to the value of gamma over p. And so what I want to plot on the vertical axis will be the amplitude, and on the horizontal axis I choose some experimentally tunable parameter. For example, I could use the power, but that's not so convenient in view of the structure of this equation, or else I simply can use the detuning, and that's an interesting parameter. More precisely, I can even do things completely generally by not plotting the detuning delta, but adding this x bar, which of course we don't yet know, that would have to be found from the other equations. But if I plot it as a function of this combination, and it is only this combination that will appear in these Fourier amplitudes, so the left-hand side plotted as a function of this is just a given. It does not depend on what in the end will be the precise value of x bar. Okay. So now, how does it look like? Well, it's obviously important to know where zero detuning is, because I always claimed that for negative detuning, that is red detuning, we have cooling. So there we wouldn't expect any instability. Only on the positive side, for positive detuning is the laser blue detuned, that is, it carries some extra energy, it can pump some energy into the mechanical oscillations. And that's true. So let me plot one particular contour line. Might look somehow like this. So that is of course something you have to do on the computer. And then for the same value of gamma over p, there will be other contour lines. They somehow look like this. And also here I will get some. Might look something like this. And so what does that mean? It means the equation is fulfilled along all of these lines. But that does not yet necessarily mean that this is a stable solution. So this is always a different matter. Once you have solved for the steady state solution, the question whether it is stable. And here again we have a very simple physical-minded criterion. Namely, when you are at some point and you go up in amplitude, in order for the solution to be stable, then the power input should diminish, because then friction will dominate and the amplitude should fall back to its value. And if you then go down in amplitude, the power input should go up, so that it overwhelms friction and in total the amplitude is pushed back towards its larger value. So that's the idea. We have stable solutions, stable attractors, if the power input divided by a square omega tilde square, that is this combination, the left hand side goes up, goes down if the amplitude is pushed up, because then it just provides a restoring force. And now if you plot this on a computer, you will quickly notice that these are really like islands, so the left-hand side would be even larger inside the islands, it's smaller outside the islands. So if I'm on the upper rim of the island and I go up in amplitude, indeed the power input diminishes, and so that's the stable part. The upper parts are always the stable parts. So these we can say indicate. Okay, so these are the stable attractors. And if I had chosen a different value for the parameter gamma over p, for example a larger damping, then I would simply pick different contour lines. For example, contour lines for larger gamma over p lie inside these because they correspond to even larger heights. And correspondingly for smaller damping, contour lines lie outside. Okay. So now there are many different features to notice about this plot. And one of the most striking certainly is that if I just pick my external parameters, such as the detuning, then I'm, say, on this vertical line, then still I can find several possible attractors, several possible amplitudes into which the system can settle. And that's called multi-stability. So it's a generic feature of nonlinear dynamical systems. Even though I fix all external parameters, and even though there is damping in my system, still there are several attractors, which is something you might not know if the system is linear, and that is, it has a quadratic potential and there is damping, it will always slide into the minimum, and that's it, and it's always the same minimum. Okay. So this is one thing to notice, and we will make a little list later. The other thing to notice is that obviously there is some instability and some finite amplitude oscillation at positive detuning, which is good, which is where we expected it to be. But also on the so-called cooling side, there are finite amplitude solutions, which is not what we expected them to be. And the reason is these are really at completely finite amplitude. So our linear analysis with the behavior of our damping rate at small amplitudes does no longer apply here. This only guarantees us that at small amplitudes down here, there is no instability. Okay. So some notes. First is the multi-stability. That is, you have multiple attractors for fixed external parameters. And what happens in reality then is that depending on your initial conditions or on the prehistory, on the full dynamics of your system, it will settle into either one or the other attractor. So that depends on the previous history. Then we remarked already that we have attractors even for negative detuning. But, and this is important, they only occur at finite amplitudes. So our linear analysis was completely valid, only it doesn't tell the full story. So if I look at the linear analysis just gave me the optomechanical damping rate. So what I found was that if I plot as a function of detuning the full damping rate, then there would be some region where it could pass below zero. And it is exactly this region which corresponds to the region here where I get some instability even at near small a. So that is okay, but it doesn't guarantee that there are no other attractors at finite amplitudes. For example, even here the attractor at finite amplitude extends beyond the unstable region, but this is okay. There's also some stable A equals 0 solution sitting down here. Okay. Now, the general structure of this diagram is relatively complicated. The diagram as shown here still depends on omega tilde if you think about it. Yeah? So from all the parameters, we already eliminated delta tilde, the detuning, because that's part of the plot. We eliminated gamma and p because we know, aha, this just sets the condition for these values to be equal to gamma over p. But what still remains in the formulas is omega tilde, that is the ratio between omega and kappa. And you remember that this was also important, say, for cooling. If omega is much larger than kappa, then this is called the resolved side bend regime. Yeah? So this is the parameter on which this plot still depends. And now, in general, it looks fairly complicated. It looks like a complicated landscape. But right here, when I start from a zero amplitude and go to a finite amplitude, the behavior is, so to speak, universal. And it even has a name. So near this threshold, what we have is universal behavior, and this going from A equals 0 to a finite amplitude is called a Hopf bifurcation. So it is this behavior. And in particular, the way that the amplitude grows is also completely universal. Namely, A goes like a constant times the square root of the distance to the threshold. And so afterwards, my amplitude grows like a square root, but the phase of the oscillations is completely undetermined. Yeah? This is picked at random depending on the initial conditions. So the same would happen, by the way, if you were to plot the amplitude versus the laser power of the drive P. Then again you would see such a plot and it would arise like the square root. Of course, you know similar plots if you look at equilibrium phase transitions, say the magnetization as a function of temperature, then below the critical temperature it also grows like the square root. And so, finally, we can ask ourselves, what happens if I'm not yet sitting on this attractor? If I'm sitting on this attractor, the amplitude is simply stable. That's what we proved, essentially. What happens if I don't sit at the attractor? Well, the point is that here the power input is larger than what is dissipated by friction, so I would always go up. Up here, the power input is less than what is dissipated by friction, so I would go down. And so that gives us the option to explore not only what are the attractors, but also what is the very slow dynamics of the amplitude. Yeah, we have the very fast oscillations, but then there is this power input that, say, slowly increases the amplitude or slowly decreases the amplitude. And I want to write down an equation of motion, not for the microscopic dynamics, but for this slow dynamics of the amplitude. And that we can do very, very easily. So what I want to find out essentially is, if I start my amplitude at some random value, then maybe it decreases in order to reach the attractor. And so, physically speaking, what happens is simply that there's a little bit more power loss than power input, so I better look at the energy. And the rate of change of the energy is simply the power provided by the radiation pressure force minus the power lost by friction. And now in our dimensionless units, the energy I can calculate simply as the mechanical energy, the potential energy given my amplitude. Okay. And that would be omega square. Okay. So now I take the time derivative of that, and I find on the left hand side, A dot times A omega tilde squared equals the radiation pressure force on average is simply P times alpha squared x dot, that's the power input, plus or minus the power lost by friction. Again, we had that before, that was gamma omega tilde squared A squared. So that would yield the equation of motion that I'm looking for. A dot equals 1 over A omega tilde squared times what I have here. And now, since this is a one-dimensional problem, I mean just with 1 degree of freedom, I can derive a potential. It's not even a particle moving with some mass or with some inertia, it's really a particle sliding down a hill. So I want to write this as A dot equals minus some coefficient times the derivative of a potential, yeah? Because that would slide down the hill. So let me choose a form that will make things look nice. I have some freedom here, so I choose A dot equals minus gamma divided by 2 omega tilde squared times the derivative of a potential with respect to A. So this is an amplitude-dependent potential, effective potential, so to speak. And so now I can just compare these equations to know what my effective potential or the derivative should look like. It should reproduce a minus sign, 2 over gamma A, and then just the expression from above. Okay, so I can write down U of A, and in particular I have one contribution from this simple damping term, and you see that the gamma cancels. That's, by the way, why I put it up here. One of the A's cancels, but if I want to get the potential instead of the derivative, I have to integrate. So what I end up with here is something very simple, and it just looks like the potential I would expect. Namely, this is just the potential energy, so to speak, of the harmonic oscillator. And yet there's an additional contribution, and that is what makes everything interesting. That is the contribution from the light field. So the idea is that this part, alpha squared times x dot, is a complicated function, the complicated function which we just calculated previously, containing all these Fourier terms, depending on the amplitude, and I would have to integrate this to get the potential. So, okay, this is something that can be done. We won't do it here. I just want to draw the potential because it reveals some physics. So I want to draw the potential as a function of the amplitude. And the potential without any light-induced changes would simply look like this. And that's very simple. So what happens here is that the amplitude particle, so to speak, slides down the potential and settles at A equals 0. That's just another complicated description of the simple damping of the harmonic oscillator. So now I switch on the light field, and what happens at negative detuning, where I expect cooling, is actually that the curvature even increases. That means I will slide down more quickly, I will more quickly damp down to a small amplitude, and that's just cooling, I get extra damping. In addition, we already saw that even at negative detuning, there is some finite amplitude attractors, and attractors in this potential just correspond to local minima. So there can be something like this at higher amplitudes. But still locally at small amplitudes it's stable, and it's even more stable than before in the sense it damps down more quickly. So this is for negative detuning. And then if I go to positive detuning and I am in the right regime where I get linear instability, then what happens is that near zero I get a negative curvature. So if I'm not exactly at A equals 0 but have some tiny perturbation, tiny fluctuations, then these will first slide down and blow up exponentially. That's the story I'm always telling. That is a negative damping constant effectively. And then it would settle into one attractor. But as we have seen, at higher amplitudes, there will be other attractors, so it can look like this. So that is a positive detuning. And so again, near A equals 0, this would be the linear instability. And that would be increased damping. And now you can play many other games with that. For example, you can add thermal fluctuations. The way to add thermal fluctuations would be to go back to your, say, mechanical equation of motion and add a Langevin force, a thermal Langevin force to that equation, and then to work out how this extra Langevin force in the mechanical equation of motion would convert into a Langevin force for the amplitude. Yeah? That's a little bit tricky actually, but it can be done. And then what you find is that you don't just sit here around the minimum, but you always fluctuate a little bit in amplitude. And if the fluctuations are strong enough, they could even take you above the barrier by thermal fluctuations, and then you have something like thermal tunneling, and you slide down again towards another attractor. So that is one idea. Another source of fluctuations, by the way, would be shot noise. So the photons have some shot noise that can also be modeled. It would sit inside the equation of motion for the light field, and this shot noise then provides a fluctuating radiation pressure force, and that can have similar effects. Okay. So finally, I want to discuss a little sort of application that works whenever you have a multi-stable dynamical system. And the idea will be the following. Say you have these attractors, and suppose you are sitting somewhere here on the attractor. And now you change some external parameter, such as the detuning, back and forth in a cycle. And let's say you choose the cycle such that you don't quite fall off the attractor. So you return to the starting point after the cycle, and that's fine. However, say your detuning might also depend on some other external parameter which you want to measure very sensitively. And if this other yet unknown parameter shifts the detuning to the right, then instead of having been here, you had been initially actually a little bit displaced to the right because of this external perturbation. Now again, you go through the same cycle, again moving right and left by the same amount, but now this has the consequence that you that you go beyond the end of the attractor, and what happens then is really you slide down to the other attractor. And now if you move back, you will just remain on the lower attractor. So the final states are completely different. Either you end up here or you end down here. They are completely different, and for example, in this particular system, they would reveal themselves by a completely different pattern of light intensity oscillations as a function of time, or also average light intensity and so on. What people call this, they call it a latching measurement. Latching is legal. So the idea is to have a measurement such that the initial and the final states are completely robust against any fluctuations. Only while you do the measurement, it sensitively depends on any extra perturbation. Okay. So that, of course, is similar to what we saw, or what we discussed very briefly for the case of the Josephson bifurcation readout, where the idea also was you have this bistable system. In that case, it was a strongly driven anharmonic oscillator, and then you would do the sweeping, and depending on some extra influence, you would end up either in the same attractor or jump to a different attractor. So that's almost the same idea. Okay. Are there any questions left? I can still add that if you increase the light power even further, then at some point you completely switch into a chaotic regime. And in this chaotic regime, simply our ansatz fails, our ansatz of saying that x of t is a simple sine function, is a function of time, that fails, and so all the analysis becomes invalid, and it's yet another very interesting regime of dynamics here. Okay. Frank?